Let's go over this AP review problem here. Number 1, let f be a differentiable function defined on the interval from -5 to 6. Now this f of x function is not shown to us. Okay, we don't have the picture in front of us. In fact, what we have is the f prime. The graph above shows the graph of f prime, the derivative of f. So we know this is going to be a derivative graph problem here. F prime has a horizontal tangent at x equals -3. The area of the region between f prime and the x-axis from -5 to -1 is 5. So the problem is telling us what the area of this region is. It's not a geometric formula that we can apply, so they're just giving that to us. F prime is a piecewise linear on the interval from -1 to 6. So we have a series of linear graphs forming the rest of f prime on this interval. And the function f satisfies the order pair f of -1 is equal to 3. So this is an order pair that exists on the f of x function, not on the f prime. But this is something that we're gonna use a little bit later on, or actually for part A. So part A says find the absolute maximum value and the absolute minimum value. So we're looking for an absolute max, absolute min on the closed interval. So this should give us a hint that we should be applying extreme value theorem, right? That this problem is trying to get the student to recognize this as an extreme value theorem problem, and the steps that we take to determine the max and mins are we consider the endpoints and we also consider the relative max and relative mins. So let's create a slope sine line so we can get a picture of what the original graph is, right? Because this is not the picture of the original graph. But if we can identify where the relative max and relative mins are for our original function, then we can gather locations of relative max and relative mins that we're going to need to test as a potential candidate for absolute max or absolute min. So what we can do is we can look at f prime and mark up or label our f prime graph so we know exactly what we're looking at. So since this is not the original shape of the graph, if we can make our mark indicating what these represent on the original graph. So on the original graph, anything above the x-axis is going to represent positive slope, right? The y-axis no longer represents the location of the graph. This represents the slope of the original graph. So anything that is in this region is going to represent where my original graph is going to be rising. So all this, even though we see this f prime graph rising and falling, on the original graph, these intervals are all going to it's going to exhibit positive slope on the original graph. Anything that lands on the x-axis is where my original graph is going to exhibit a slope 0. And anything below the x-axis is going to represent where my original graph is going to be falling, where there's a negative slope. So we know that, first off, there's a critical point at -1 and 2, and also endpoints at -5 and 6. These are places where slope 0 are. So that's where I mark my critical points. From -5 to 1, all this is above the x-axis, so I know that it's going to translate to be a positive slope on the original graph. So here I have positive slope. Between -1 and 2, all this is below the x-axis, so negative slope. And then between 2 and 6, above the x-axis, so back to positive slope. Okay. Now we know that we're only having to test these 4 points, 2 critical points and endpoints, as potential max and mins. Right, so we have to be able to know where they land on the original graph, and this is an order pair that's going to help us out. All right, we know f of -1 is 3, and through a series of finding these area regions, we can use this formula that final position is equal to initial position or the given position plus displacement. So here's my formula here. X of b is equal to x of a plus the definite integral from a to b of x prime. So now what we can do is we can go through this process to find each of our 4 points. So f of negative 5. So if I want to find f of negative 5, I'm going to start off always with f of negative 1 because this is my anchor point. This is the point this is the only point that we know on the graph, and we're going to have to build everything off of this information. So f of negative 1 plus the depth integral from negative 1 to negative 5. So notice how we're going backwards here because we always have to start at the given point with a lower bound, and then we have to move to wherever our destination is. So sometimes if it's going forward, then it's fine, but if it's going backwards, we write it out what we have with our formula, but then if we're reading a graph, we may have to make some adjustments later on. So the adjustment that we have to make is the fact that it's easier to read the graph from left to right and not have to change signs in our heads. So let's go ahead and change the sign here, or reverse the bounds so that we can actually read from left to right. So negative 5 to negative 1. And then we're going to change that plus to a negative. We change that sign. So we have f of negative 1 being 3. And then now we're going to total the region between negative 5 and negative 1. So between negative 5 and negative 1, well, we're given that the area is 5. So we just have to replace the depth integral with positive 5. Now, once we do that, there's a negative left over because we changed the sign of because of the bounds that we switched. So now we get 30 minus 5, which is negative 2. Okay, so we have f of negative 5. That's going to be a candidate. Next up, f of negative 1. F of negative 1 is already given to us. It's equal to 3, so we can just put that down and move on. F of 2. So f of 2. Go back to our formula here. F of 2 is equal to f of negative 1, right? We always have a starting point that's using the initial that's given to us, plus the depth integral from negative 1 to 2. Now, negative 1 to 2, this is in order from smaller to larger, so we can just leave it the way it is and just read the graph. So the graph from negative 1 to 2 is just this triangle here. We can figure this out using a geometric formula, 1/2 base times height, 1/2 3 times negative 2, because 3 is my base, 2 is my height. This is below the x-axis, so I get 3/2, or sorry, I get positive 3 with area, but because this region is below the x-axis, I made that adjustment to be a negative 3. So then f of negative 1 is 3. The depth integral from negative 1 to 2 is also 3. It's also, sorry, negative 3. So 3 plus a negative 3, 3 minus 3 is 0. Okay. And now let's look for the last order pair, f of 6. F of 6 is f of negative 1, right? Starting point, plus the depth integral from negative 1 to 6. So negative 1 to 6, we're going to have to total all these regions here. So from negative 1 to 6, well, I guess we could just, we don't have to go through what I did here. I found each of these regions separately, but we could just find the area of this entire triangle here. This is a base of 4, right? And a height of 4. So 1/2 4 times 4, that's 16 divided by 2, which is 8. Okay. So we know that this full area is 8. So if we total all this up, we get starting point is 3, minus 3 plus 8, and that gives us just 8. So now our by extreme value theorem, we can therefore conclude through the work that we've shown and information that we've gathered, our absolute max value must be the highest y value that we see, which is 8, and this happens to be located at x equals 6. And the absolute minimum value, the y value, the lowest y value that we see is negative 2. So the absolute minimum value is negative 2, and the location happens to be at x equals negative 5. Part B, write the equation of the line tangent to the graph when x equals 5. Using this tangent line, approximate f of 5.1. So let's go through the steps for linear approximation. So for linear approximation, we need to first find our slope, find our point, and then we can create our tangent line equation. There's y minus y1 equals m times x minus x1. And then once we've gathered our tangent line equation, then we can plug in that decimal value, which in this case is 5.1, and for the x. And then we get to our decimal value, and that decimal approximation, and that is our answer. Okay. So we need to find ordered pair and slope for our functions. So the ordered pair at 5, now we can't just look at this graph and just say, well, at 5, that's 5, 2. That's f prime. Okay. So what we need is we need to find the definite the ordered pair for f of 5. So we're going to have to go through this formula again. This final position equals initial plus displacement. So initial is f of negative 1 plus the definite integral from negative 1 to 5. Now negative 1 to 5, I have to break this down a little further here. This is a triangle with area 4. I guess we could do a trapezoid formula, but another way that we can do this is to help separate this. We know that this is a triangle of 4 because area 4, 1/2 base times height. But then we can also recognize this is also area of 4, right? This area and this area is the same. And then if I find the area of this triangle, 1/2 base times height, 1/2 1 times 2, that's going to be 1. So if this triangle, this smaller triangle is 4 and this little triangle is 1, then 4 minus 1 must be equal to 3. So I can figure out that region without having to go through a separate trapezoid formula, just by subtracting the smaller triangle from the larger triangle. So we know that the definite integral from negative 1 to 5 is going to be negative 3 plus 4 plus 3. And so sorry, the negative 3's will cancel out, which is left with 4, and f of negative 1 is also 3. So 3 minus 3, 0, plus 4 plus 3 is 7. So we have our ordered pair, which we found going through this formula, being 5, 7. And now we need to find the slope. Now this is the f prime graph. So with f prime of 5, we can just look for the slope of f of x by looking at the ordered pair. So because we're looking at the f prime graph, we can just pick out the ordered pair. So f prime of 5 is just going to be 2. So we have our ordered pair at 5 7. Our slope is at 2. So then we just put into our formula here. All right, so y minus 7 is equal to m times x minus 5. So let me just highlight that information again. Our ordered pair is at 5, 7. And then our slope is 2. So we have our ordered pair, we have our slope, and then we put into our point slope 4. Y minus 7 is equal to m times x minus 5. We have our tangent equation. And now we just take that equation and we dump that decimal in. So that 5.1 we'll plug in for x, and then we can work this out by hand or use our calculator. We get 2 times 0.1, which is 0.2, plus 7, which is 7.2. All right, part C. Suppose that our definition for g of x is the definite integral from 3 to x of f prime. Find g of 3, find g prime of 3, and find g double prime of 3. Well, let's go ahead and find each of the definitions or formulas for g of x, g prime, and g double prime. We already have g of x, so let's just go ahead and find g prime and g double prime. If I want to find g prime, I need to take the derivative of this and create a situation that represents the derivative of this mess here. So if I want to find the derivative of this expression, we see these are two inverse operations. They're going to cancel each other out. We can apply second theorem, which allows this to cancel out. We just plug this upper bound into the variable. We get f prime of x. So there's our formula definition for g prime. G prime is just going to be f prime. And now if I want to find the derivative of g prime becomes g double prime, and therefore we can just follow that form. F prime is f double prime. So g of 3 is just the definite integral from 3 to x, 3 to 3. We just replace the upper bound with whatever x value we have here. Now, as if our lower bound and upper bound are the same, there's no area for us to find, so that's always going to be 0. Okay. All right, moving on to G prime of 3. G prime of 3 is just F prime of 3. F prime of 3, we can look at the order pair on the F prime graph. So F prime of 3 is just going to be equal to 2. That's order pair 2 sitting right there. G double prime of 3 is defined as F double prime of 3, and F double prime of 3 is just going to be the slope of the F prime graph. Right, the slope of the F prime graph. Now, F double prime of 3, we're looking at the slope of the F prime graph at 3. This is a linear graph, so we just find the slope of this line, which we can do change in y over change in x, or we can do slope up 4 over 2. So that's the slope of 2. So the slope of that line is 2. So that's going to represent G double prime of 3. All right, last part here. Evaluate this limit. So whenever I see like a messy limit expression, that should give me an indication that this is probably going to be a L'Hopital's rule. But we have to confirm the condition that is required for L'Hopital's rule to work, and that means the numerator has to produce 0 and the denominator has to produce 0 when we evaluate the limit. So let's do limit as x approaches 2 of the numerator. So we're going to do this separately. So limit as x approaches 2 of f prime of x is equal to f prime of 2. F prime of 2, we look at our graph. F prime of 2 is just equal to 0. All right, so the numerator does produce 0. Denominator, limit as x approaches 2 of the denominator. I'm going to write this whole denominator expression out. Evaluate the limit, so plug 2 in for x, we get e to the 2 minus 2. E raised to the 0 is just 1. 1 minus 1 is 0. So numerator 0, denominator 0. The condition is set for L'Hopital's rule. So L'Hopital's rule says if I have a 0 in the numerator and a 0 in the denominator, once I evaluate, I can take the derivative of the numerator denominator and then reevaluate. So here's my limit expression again. I'm going to take the derivative, so f prime becomes f double prime. E to the x minus 2, e to the u is just e to the u times u prime, so e to the x minus 2 is e to the x minus 2 times x minus 2's derivative, which is just 1. And the minus 1 is a constant, so that just goes away to 0. So I didn't put anything here. I just left it blank, since 0 just goes away. Now that I have my derivative notation expression, I'm going to reevaluate the limit. So replace every x with 2. F double prime of 2 over e to the 2 minus 2. E to the 2 minus 2, that's e to the 0, which is 1. Now f double prime of 2 is looking at the graph to figure out what f double prime of 2 is. Not f prime of 2, which is the order pair, but f double prime of 2 is the slope of this line. Now the slope of this line is just going to be a slope of 2. If I pick any point here, I go up 2 over 1. This is a part of a line that has a slope 2. So that's enough for me to make that substitution. So 2 over 1 is equal to 2. That's a real number, so that's our answer.